Mic is not on. Is it on? Can people hear me? Great. Okay, let's start. So we live in an era where apparently AGI is like 18 months away, or maybe it is 16. I mean, we don't know. But there is a certain narrative where the frontier models just continue to hyperscale, and the new innovation that is needed is just let's deal with multimodality, so we can call them VLMs, and then the next is let's add in action, and it's VLAs. But there are rumblings of dissent, okay? And that's why I titled this AI and its discontent. So there is, for example, the talk about the era of experience. So this is from Rich Sutton, and he's arguing that this is not autonomous learning. This is just memorized regurgitation of some form. There is the line of work which goes under the rubric of world models or dynamics models. And then even people who started the hyperscaling trend, people like Ilya Sutskever, have been talking a lot about continual learning, which is not what is there in current day systems. Once a system comes to the general public, it does not learn anymore. So I want to offer a small take on that. I won't spend too much time on it because I want to be mostly talking about robotics, which is a very concrete case. But here I want to refer to this paper. This is a position paper. It's very speculative, written by Emmanuel Dupont, Jan, and myself. And the title is Why Systems Don't Learn and What to Do About It. And I think the lion's share of the credit goes to Emmanuel. And what we tried to do was we tried to bring in perspectives from AI and cognitive science, critique the current state of business, and then offer at least a half-baked or quarter-baked theory of what needs to be done.
What year was that?
A few months ago. Yeah. Right. Okay. So So first, what's a critique of the current stuff? So the current stuff, this cartoon, which is of course generated by an AI, is a critique of standard machine learning, which is a very, very engineered kind of system, right? So you typically, in a frontier lab like, say, Google or Meta or OpenAI, you'll have a few hundreds of people. What they do is they spend most of their time curating the data. And then there are these various stages, the pre-training stage, mid-training, fine-tuning, the RLSHF stage, et cetera, et cetera. So it's all kind of like a very delicate system with lots and lots of art, one should say, which is very different from how learning operates in humans. It's an autonomous, it's at the level of an individual, whereas in the standard pipeline, what we are talking about is just ingesting the content of a culture, as Allison would put it. And so we want to go back to that perspective, that autonomous learning for an agent, and hopefully simplify things as well. Okay. So the way we do this is that we are So think of it as a cartoon model, right? It's capturing some big ideas, but it's not going to be operational in detail right now. So we are arguing that you should think about it in terms of three systems: System A, System B, and System M. Okay, so let's talk about System A and B first. This is different from System 1 and System 2. Those terms are already taken up by Kahneman, right? So we are not using System 1 and System 2, and this is a very orthogonal distinction. So roughly speaking, System A is a system which is based on observational learning. So so imagine the baby or child just observes, okay? And their language can be like that. So they're just always hearing a stream of language and doing some kind of self-supervised learning on top. You could be doing the same thing with respect to video, because the child initially, let's say most of what they see about the world, they cannot affect themselves. So they observe, so they see frame after frame of video. The world is just flowing by, and you're building a model of that. So in the case of language, that's a standard term. Language model the idea goes back to Shannon, 1951. Given the past so many words, you try to predict the next word. In the case of video, it would be given the past so many frames, you try to predict the next frame.
The baby can still move its head or eyes.
Sure. I mean, it's some, but I mean actively changing the world. Okay, so that part we are pushing into system B. So system B is where you are acting in the world, getting rewards, and continuing. And there is a value in having these two systems. So for somebody who comes from the reinforcement learning, Markov decision processes, control system literature, it's all about system B. That's what those models are. And in that, certain aspects such as what is the dynamics model, what are the rewards, are treated as exogenous. They're just written down and you solve the problem given that. Now for an agent that cannot be the case. We have to bring exogenous things to be endogenous in some form. Now this is where system A comes in, because you build models of the world. So if you are going to act in the world, your observations can help you build a model of the world. Okay. So
Jitendra, where does verbal learning cut? Is that in system A then in this framework? Like if somebody's giving you instructions?
I'll come to that. I actually have a slide on social learning, so I'm going to get into that. Yeah. So I just want you to get this big picture here. Roughly speaking, A is observation, B is interaction, but there are many cases of this. We can talk about children learning language in this way. They're observing, language or speech in this case. They observe. They're always hearing the language stream which is there in their environment, the parents and so on and so forth, right? But then they have to master their vocal articulatory apparatus, their vocal cords, the lip, the tongue, etc., from which they have to produce sounds which at some point start to match what they're hearing. So that's the part where they are practicing speech, babbling, that is system B. The part where they are just listening to the sounds in their environment, that is system A. And these two obviously interact. Okay, so with this cartoon version, I will move on. And then at the end, I'll talk about the role of system M. Okay, and now I'll get concrete, and this high-level philosophy to me applies for many things. It applies for speech, I think it applies for the songbird example, it applies for motor control, for robotics, learning how to act in the world. Pretty much everything should fall under this umbrella. But now what I'll do for the most of the talk is to focus on robotics, acting in the physical world. Now, here first is a high-level view of how to think about robotics. You should think about it at multiple levels. There is the highest level, which is the level of goals and plans, a middle level, which we could call the level of Aristotle. Okay, goal-directed. There was this GPS paper from the AI people in the 1950s, but Aristotle had talked about means ends analysis 2,000 years ago. There's a level of motion trajectories in 4D, which you could think of as Euclid, and then there's forces and torques, which you could think of as Newton. Okay, let me be more concrete. So let's start with goals and plans. Okay, you want to make an omelette, let's say. That's a very concrete task. You can type this question into Gemini. In fact, I did. You get an answer like this, right? And now there's a sentence there, crack eggs into the bowl. Now that is where you need to elaborate to the next few levels. So I have this pseudo equation, which I think is helpful. Action equals movement plus goal. So to achieve any action, every action involves a physical movement in space, but there's a goal behind it. We are trying to achieve some goal. So we'll have so language emphasizes goals and plans, but movement in space and time are equally important, and we need to capture this duality. So this is what I mean by movement in space and time, right? You're trying to perform some task, and then let's break it out into the atomic steps, which are at the level of 1 or 2 seconds. Then these will be the kinds of movements you have. And these you can observe. You can observe other people do these, right? Okay. If you go to a longer time intervals, then essentially this set is infinite. For a shorter time interval, you have the hope of getting the equivalent of phonemes for movement. Yeah.
In the case of acting to explore, are you think of curiosity or exploration as the goal? What is the goal?
I haven't talked about that yet.
Okay.
Yeah. I mean, okay. Then, but this is not enough. So these movements in space and time, F equals ma strikes, right? To change things in the world, you have to apply forces. Those cause accelerations. Those cause changes in trajectories. Now, in the human sensory motor system, we actually have so like simple tasks like picking up an object. There will be various forces applied. Normal force, you need to resist gravity, so you need to have enough friction to compensate for gravity. At the bottom, you have the neural outputs of various tactile and proprioceptive sensors, which have to be inputs for this. So this is the third level. So I think we are not going to solve robotics until we give equal respect to all three of these levels. Okay, so then that's the question. How should we train robots? And the cliched answer, and I think it is a fact that robotics is well behind natural language processing and computer vision. In the beginning, I used to say this, and robotics people used to get annoyed, but I think it's just factually true. And it's for a good reason. In fact, it's because it's mostly not, there are problems to be solved which are to do with shortage of data, and only when we solve them will we be able to solve robotics. And here are the three leading paradigms. I think I find them all unsatisfactory, but these are the current state of the art, so let's review them. So this is what teleoperation is. So you essentially have a human teleoperating a robot. So you are like a puppeteer. So this person is operating something which is copied in the follower system, and then you're trying to extract a paper towel from, right? Why is this? So this is what is done today. So this is the main formula, and there are thousands or maybe millions of people collecting data like this all over the world.
But isn't this also a way to collect training data?
Yeah, this is for collecting training data.
Okay.
I mean, that's what people do. I mean, this is the dominant paradigm. Okay, let me say why I dislike it. Okay, I dislike it because of two reasons. I mean, it has certain advantages. It directly gets you trajectories, and then it converts a problem to a supervised learning problem, which is a formula which has worked well in other settings. The problem is, one is human sensory motor limitations, because the human it doesn't get full haptic feedback and so on. So the human is trying to use their vision system. So it adds like 200 milliseconds of delay. So you're just very clumsy and slow with this. So the trajectories collected with this are just like much slower than what either the human would be or the robot could be. So my joke on this is like tying a horse to a car. And the horse could run fast, the car could run fast, but when you tie a horse to a car, you're going to inherit the limitations of both systems. Okay. So this is the dominant paradigm. Second idea is that let's learn from video, which we could collect. So this is also being done by thousands and millions of people. So you collect egocentric video. And these are examples of this. And, so in my role, I work part-time at Amazon. In my role there, we have all these companies who approach us who are selling this kind of data. Okay. And what's the limitation there? So this data is at least natural. Humans are being humans, not humans are being robots. But the challenge is that humans are not the same as robots, so there's an embodiment gap. So the trajectories are not going to directly be translatable. And then there is missing information. So you do not have force information. And forces are important. If you are going to act in the world, a robot acting in the world has to know about forces and talk. So that's a limitation. Then finally, we have simulation. And simulation, you can have access to forces, trajectories, everything. The problem, of course, is the limitation of simulators today. that they are not perfect. So that's the so-called sim to real gap. This, I think, is an engineering problem which is just getting better over time. People just build better simulators. So I think the situation now is better than it was 3 years ago, and is better than what it was 10 years ago. And it's proved this formula has succeeded for locomotion. Robots which walk have been trained in simulation and then put zero shot in the real world, and they work. So we define, but this is a more subtle argument which actually holds things up, which is the problem of specifying the task. So we define it as a reinforcement learning problem, which means that you have to specify rewards. Now, here's what I want to do. I actually want my robot to pick up this water bottle and pour something, right? I have to convert this into the language of reward terms for reinforcement learning. And this is what you land up doing. You land up writing zillions of these terms. There have to be coefficients for these terms. You might need 100 terms. And this is what kills this line of work in practice, right? Whereas there is a trajectory which you want to copy in some form, but we have to specify it this way. And this is why the community jumped on this teleoperation bandwagon, because on teleoperation this problem just goes away, right? I mean, all of these are in. So the human knows the task, and the human executes a task. So in that sense, the specification is being done by the human implicitly. So the problem is solved. Okay, so now I'll go a little bit into the approach I favor, and this is basically, in fact, was stated by Turing in that famous 1950 paper. It's in section 6. People usually read only section 1, or they claim to have read section 1. But there is a line there. Instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? If this were then subjected to an appropriate course of education, one would obtain the adult brain. This is 1950. Today is 2026, 76 years later. But I really think this is the right way to think about it. And of course, in the last 76 years, our colleagues in psychology have not been idle, and they have done a lot of research from which we have insights into how to make this kind of a program concrete. And I've picked one paper. I mean, think of it as a review paper, but obviously there's a huge literature. And I won't go into too much details, but here are some vignettes of insights. Multimodality is very important. Use multiple senses at the same time. There's a natural curriculum, which in biology, embodiment matters. There's a explore, exploit. Many of these topics have been discussed in the last week. So I think all of these have, there is a lot of merit in this. There is no I cannot reduce it to one simple-minded, a one-line formula. I think all of these aspects are important. Reality requires this. So now let's talk about how we can operationalize this, and now I'll answer a bit of that social question. So this, to me, this is a cartoon picture of how I think about some of these things. So here there's this baby girl observing her father wash dishes. So this is a way, there is some cultural transmission going on. So the big idea that, okay, you have a pad, it's soaked in water and soap, and then you rub it in a certain way to clean. So that she doesn't have to discover by trial and error. She is getting cultural transmission of that. But she cannot just do it. She doesn't, lots of information is missing. Information about forces is missing, for example. And then her body is not the same as the parent's body, right? So there's missing information, and then the body is different. So therefore, there has to be a process of translation, or retargeting is the term we use in robotics. And this part has to be an active process. So this is what is going on here. So she's playing, and in this play, she discovers how her own body acts. So she's discovering a, quote, world model of her own body. But she's guided by what she observed, right? So this is a little bit of the system A and system B here in one setting, but with a social aspect here. Okay, so this is what I believe. I think that if we can make this happen, this is, in my view, the recipe for scaling up robotics. Now, how do we operationalize it? So we actually have done one version of it already. This was presented last year. This was for locomotion, and I'll just show you the video. Okay. So this is, you'll soon recognize various iconic Berkeley landmarks. Okay, so this paper is called Video Mimic. And, okay, I should raise the volume. Okay, so it looks a bit drunk, but so this is what is called perceptive locomotion. So it's actually using its vision system. Locomotion is mostly 90%. I don't know. You can if you train for longer, probably all those will go away. But I mean, these tasks like stairs and so forth require a vision system, right? Otherwise, normally walking on flat ground, you don't need vision. It's really about proprioception. Now, how we trained it? We have data of humans doing these tasks. So these are various grad students in the neighborhood of various Berkeley buildings. Okay, so there's data of humans doing this task. Then we go through lifting this data of humans walking into 3D. Let me actually move to this. So there's a video of a human doing this. Okay, then you reconstruct this in 3D. So this is a computer vision problem. So we can lift the human to 3D and the environment to 3D. And now you have to do the retargeting. So this is the task where the girl has to do in her body what she observed her father doing. So in this case, the girl's role is being taken by the robot. Okay? And so imitation learning is actually a very active process. It's not just replay. You have to do it actively in your own body with a dynamics model which you have acquired through play or practice or whatever. So that's a picture. These are more details, but now you can in fact simulate. You can also solve the ego versus exo problem, right? So we always observe in exo, but we have to act in ego, and that perspective difference. Well, it turns out that if you have a 3D model of the world, then you can always go from ego to exo to ego, whichever way. It's totally straightforward. So anyway, these are just more examples, but I think the point is clear, right? So this has succeeded. I think this is the way the business of humanoid locomotion now, I think, is more or less like an engineering problem that the companies are executing on quite successfully. Okay, manipulation is still hard and mostly not quite done. There'll be nothing to the level of human competence. And back to this picture. So now we want to do this for manipulation tasks. So I'll show you some, I mean, this is a paper we submitted like 1 week ago. So it gives you a flavor. So at the top, this paradigm would be, at the top we have these pictures which show humans performing some tasks. So you have videos on YouTube. And at the bottom we have this done by a robot, right? But I think a video would be more convincing. So let me play this here. Okay, so that's a human version. This is the retargeted version by the robot. And you should not get convinced by this that this problem is solved. These are cherry-picked examples. Okay, I'm being honest about it. But it gives you the flavor of how the game should be played. Okay?
Does that robot have a visual input?
This one, no. But, I mean, it can. I mean, that part is straightforward, right? Because you can build a model of the 3D world. So.
Does proprioception not matter?
Proprioception is everything.
Because you don't have it from the video.
No. So right. So proprioception has to be in the body of the robot. Yeah. Because essentially, look. So you translate in the 3D world, and now when the robot is going to act, it's going to act with its proprioception as its 3D sense. Okay. Then yeah, these are more examples to show that there's diversity in this. These are actually, this model is incomplete in a very vital way, which is that this is just open loop playing of a trajectory. What you really want is one which is closed loop by using tactile signals and visual signals to feedback. And that's what is needed to make this robust. But this gives you a flavor of that I think we have succeeded, at least in these examples, of doing the retargeting from observing the human to in the body of the robot.
So
Mikhail.
when you try to generate imitation of a person, you have to have an objective function, right? What is a good imitation and what is not? Why not use something like a GAN, a generative adversarial network?
I hate GANs, but I won't go into.
I know you hate GANs, it's okay. But you don't give it but you say, here is the original video.
Okay.
Here is the imitated video by the robot. You tell me if you can distinguish between the two.
Okay,
And as
so
long as
Mikhail,
you
we'll
can,
have to
you
answer this question later. Yeah, because she's telling me 5 minutes.
Okay.
Yeah, okay, so this is trajectory imitation in the 3D space. That's what we are doing, okay? And we can do this for a variety of actions. Anyway, now I should tell you what goes in underneath the hood. Underneath the hood is decades of research in computer vision. And so like for hand reconstruction, there was this model called Hammer we released a few years ago. There was work we did on HMR 2.0 with Anju Kanazawa and George Pavlikos. So those models are out there, everybody is using them. So that's why we can do 3D reconstructions of hands from a single image with fairly high fidelity. This was something we did at Meta, and this is called SAM3D, and this enables one to do 3D reconstruction from a single picture. So I'll show you the demo here. So that's just one image, and then this is how it's been reconstructed. And the reason it works is because it's reconstruction via recognition. Once you recognize this object to be like a chair, and you have seen many chairs before, so then you can do the conditional generation of the 3D shape. And this took a lot of work. I mean, there's a line of work in computer vision which goes back to Larry Roberts, the first PhD thesis in computer vision, but finally we can do it. I mean, okay, and these are more examples of reconstruction. Now I have a few minutes to go, so I'll show you examples. So the critique of what I showed you earlier was that this was just an open loop replay of a trajectory, whereas what you want are controllers. You are sensing and acting. And so those can be built in simulation. So once you take this trajectory, put it in a simulator, now there you have physics. So it's a physics simulator. And now you can put perturbations and respond to them. So these are examples of some policies. I mean, this is a separate project, but I think these can link up. So you'll see some demos of humanoids doing various things. Okay, I'll move on. And here you can get robustness. You cannot get that in an open loop policy, but here you can apply some disturbing forces, and then the policy has to be robust to that. Okay, 1 minute on the fourth story. So humans have sensing for this. So we have sensors in our joints and we have sensors in our skin. So for some time we were working on the hardware aspects of it, building these sensors. So this was a team at Meta which did this. And one can build amazing sensors now. So on the right is the human skin, and underneath there are these varieties of sensors underneath your skin surface. And we can do a version of that in technology. The challenge, of course, is to use it, the downstream part, the brain part. And we have like the beginnings of results. So this is a project where this was in collaboration with Sharpa, which is the leading manufacturer of robot hands, and you can see various of these wiping type of tasks where delicate force measurements are needed. My belief is that if you use rich sensing, the complexity of the problem comes down significantly. So why we need all these thousands or 10,000s of demonstrations with teleop is because we are not using rich sensing. Once you use better sensing, like properly use proprioception, properly use tactile sensing, I think the complexity comes down. Biology, in the old days, robotics people tried to stay away from complexity. And the reason was because they needed to have these linear models and then design controllers analytically. Once you have the era of learning and so forth to develop controllers, you're liberated. And now complexity is no longer your enemy. Rich sensing is good for you. And I'll kind of skip this. This is some more recent work which is on learning to peel vegetables. And here it turns out that you can do feedback, give feedback on how well the policy is doing. So this is the teacher part. So a teacher observes you doing a task and then says, this was good, this was bad. And this was, I again, don't have time to go into details. Some high-level remarks. I think that this is what robotics should focus on. These atomic skills, which are like, and once we master these atomic skills, which are in an embodiment, then the composition part is where language and higher level stuff comes in. But master the atomic skills which do require acting in your own body or in the robot's body. Okay, back to the very big picture. So I think this slide, which is a bit busy, is trying to show that the various ways in which we learn. So we learn by observation, but we also learn by teaching, which is this social signal where you're observing someone else doing the task. And then, but you have to solve this problem of this ego-exo transference, which is because you observe in exo, but you have to solve in ego. And then, okay, now this is a more hand-wavy part, like how do the system A and B interact? Because one provides data for the other, one provides models for the other. And we are saying that this is where meta stuff comes in at the top level. And please read the paper for more details. I think this is more like laying out an agenda for research rather than a concrete solution to the problem. But I think it hopefully gives some insight and clarity. Thank you very much. Question, yeah.
CVPR, there was a couple of hot takes about explicit 3D representations. And many of the methods you demonstrated included explicit 3D, so you lift the
Yeah.
Do you think these are...
Oh, okay. Yeah, so the question was about explicit 3D or not. So I find that I saw that